All right, guys, here we go. This is going to be a great question. This one we're even going to have to draw a picture. How about them apples? Here we go. We got a body of mass 4.2 kilograms with an initial speed of 5.6 meters per second, beginning to move up an incline. Let's draw that picture. And there we go, moving up the ramp, that mass with that initial speed. The body will be brought to rest at the top of the 0.85 meter tall ramp by a compressed spring. So it's going to be going up fast enough that by the time it gets up to the top, we're going to have a spring up here. It does tell me in the next sentence here that the spring constant here is 1,000 newtons per meter. And it also tells me that the ramp is 0.85 meters tall there. All right, so here we go. We are ready to answer this question. We're going to go ahead and start with our energy equation. Now, the reason why we're doing energy equation is because I got something that's moving. It's changing its speed, it's changing its height, and there's a spring. All of those are pretty dang good indications that we're going to do conservation of energy here. And so we've got the work, change in energy, plus the change in gravitational potential energy, plus the change in elastic potential energy. Now, right off the bat, we do see that it says assume the ramp is frictionless. So we're going to look at the block earth spring system, because that means that both the gravitational potential energy and the elastic potential energy are going to be internal to the system. And so the only other forces could be friction, but we just said it's frictionless, so no friction. And then the normal force of the ramp, but the normal force of the ramp will be perpendicular to the motion, so therefore it doesn't do any work. Therefore it's not necessary in our equation here. So therefore, all the forces are accounted for. Gravity, the spring pushing on the block later, that's all internal. So no work is being done. So we'll go ahead and put a 0 in for the work. And then we'll take the final kinetic minus the initial kinetic, the final gravitational minus the initial gravitational, and then the final elastic minus the initial elastic potential energy. Now, which of those can we cancel out? Well, we do know that it starts with some speed, so that initial is going to be necessary. It does say that it is brought to rest, which means that final kinetic energy will be 0. Okay, if we define the beginning height down here as 0, then we know that our initial gravitational potential energy is 0. And then the elastic potential energy at the beginning is 0 because the spring isn't being compressed or stretched at all. So we this time have 3 different terms, right? We're going to have that negative 1/2 mv initial squared. We're going to have that mgh final. And then we're also going to have that 1/2 kx squared, where that is the final compression of the spring. Now, you'll notice this just means that the block is going to go up the ramp. It's going to lose some of its kinetic energy to potential energy because it's increasing the distance between it and the Earth. And then it's going to run into the spring, which is going to cause that final kind of compression there. All right, so that's what we're going to look at. We're going to go ahead and throw in as many of these numbers as we can. So we got negative 1/2. Notice again, we cannot cross out the mass. It's tempting to because we could when we did the kinetic and the gravitational potential energies, but we can't do that here because we have the elastic potential energy, which does not have mass in it. So we'll go ahead and put the mass here, that 4.2 kilograms, and then we will take the initial speed, which was 5.6, square it. We'll add that 4.2 times the g, which is 9.8, times the height, which is at 0.85, plus the 1/2 times the k, which was given to us was 1,000, and of course times that final x squared, which is the question, is how much is the spring going to be compressed. All right, now we'll go ahead and work this. Let me just make a quick note here. You may be tempted to use forces or something like that here because, you know, you could find out the acceleration of the block going up the ramp, by looking at the force of gravity and that horizontal, right? We've got, you've got the normal force going up this way, and you got the force of gravity going down that way. So it's tempting to try to get this horizontal piece of gravity. Now, we have two problems. Number one, we don't know the angle. And so without the angle, you're not going to be able to find that anyway. But the second problem is when you get up to hit this spring, the force of the spring is always changing. Remember, the force depends on how much it's been compressed. So when it's been compressed, you know, 1/4 of a centimeter, the force is different than when it's been compressed 1/2 of a centimeter or a full centimeter. And so we can't really deal with that without calculus. And so at this point, energy is the best way to go. So that's my little caveat saying, you know, this is why we didn't do the forces at the beginning. It's important to recognize both why we're doing something, but also why we're not doing it. Okay, so we'll go ahead, and at this point you should be able to do the algebra. Hopefully you were doing it while I was doing my little mumbo jumbo there talking, and this is hopefully what you got for x. 0.248 meters. Now, we do only have one significant figure up here in the spring constant. Because that's the case, our final answer should be 0.2 meters. And there we go. That should be your answer. Ta-da!